So we're focusing on two of these possible intermediates, the ones where you have the positive charge and one of the resonance structures on carbon 1, on the carbon of the carbon of the substituent. And you get this when you have either attack at the ortho or at the para. So what would be called ortho-para attack or 2,4 attack. Now let's think about that substituent. Okay, if this substituent has a negative I effect, it's going to be sucking electrons away. But it's very hard to suck electrons from something that's already positive. Okay, so this intermediate is going to be very, very destabilized when you have a negative inductive effect on there. So destabilized that in fact it's probably not going to happen. Okay. Conversely, of course, if this substituent here has got a positive inductive effect, it's pushing electrons in. Well, there's nothing a positive charge likes more than having electrons pushed towards it. So this intermediate, more than any of the others, would be stabilized by having a positive inductive effect. Negative inductive effect is always bad because it's sucking electron density away, but it's particularly bad when you have 2,4 substitution, because then you're losing effectively one of your three resonance structures. Now in the same way, of course, any of the intermediates are going to be destabilized by negative mesomeric effects. Trying to suck electron density away from the ring is bad anyway. Trying to suck electron density away from a ring that's already positive is even worse. Okay, so intermediate's going to be destabilized by negative, inductive and mesomeric. All intermediates stabilized by positive inductive, but particularly this intermediate stabilized by positive inductive, pushing electrons towards that positive. But the real cool one is when X has got mesomeric positive effects. And in particular, let's just illustrate it by having a lone pair here. It would work just as well if I had a pi bond, but it's much more effective in general when you have a lone pair, because now you've got a pair of electrons here on this substituent X. That pair of electrons can of course help stabilize the positive charge, just like we talked about when we talked about mesomeric effects generally. So that lone pair can pop on in there to give you that fourth resonance structure. And for this one here, for the para attack, it can do the same, giving you a fourth resonance structure. So when you have a positive mesomeric effect, then you can have a fourth resonance structure when you've got the 2 or the 4 attack. So positive mesomeric effects means that 2,4 is much better than 3. Negative mesomeric effects mean that 2,4 is really bad compared to 3. So let's see if we can put all this together in one big chart. Okay, we can have 2,4 directing activators. So these are substituent groups that activate the ring. So that means positive mesomeric effects and or positive inductive effects. Okay, and then they're 2,4 activating because the 2,4 is particularly nice when you've got electrons coming into the ring because of these two resonance structures. Positive inductive effect pushes electrons towards the positive charge. Positive mesomeric effect gives you a fourth resonance structure. Remember, the more resonance structures you can have, the better it is. Okay, so the 2,4 directing activators are as follows. First of all, we have all of these first three here. These first three lines here are all going to be ones that have a negative inductive effect because you've got nitrogens and oxygens bonded to the ring, which is nasty, but they've got a really big positive mesomeric effect. So the positive mesomeric effect takes care of the negative inductive effect. Carbon-carbon double bond down here, of course, has both positive inductive and positive mesomeric, but its positive mesomeric isn't that big compared to the positive mesomeric you get from these. So that means that when you've got a nitrogen coordinated, it is a very, very strong activator. When you've got an oxygen coordinated, it's very strong. When you have nitrogen or oxygen that are having extra inductive effects because they've got extra oxygen atoms there, those are only strong, and then the carbon-carbon double bond is weak. Then of course you've got little alkyl down here. I don't know if you've noticed my color coding in a way, but the alkyl group only has that positive inductive effect, and it's a weak one. So methylbenzene, more reactive than benzene, only just. Put an OH on there, phenol, or an NH2 aniline, very reactive compared to benzene because they're massively very strong activators, and it doesn't matter what activator you have, all of them have 2,4 directing. In other words, the substitution will be at the 2 position or the 4 position because of the extra stability afforded to this resonance structure, or because of this extra resonance structure here. Now halogens are kind of fun. They're 2,4 directing deactivators. Okay, they're 2,4 directing because they have positive mesomeric effects, but they're deactivating because, if you remember, their negative inductive effect overwhelms the positive mesomeric effect. Because we've got a conflict there, one good thing, one bad thing, while they're deactivators, the bad's better than the good, they're weak deactivators. All other deactivators, though, have got negative mesomeric, negative inductive. Negative inductive means that these are really destabilized. So effectively, when you get 2,4 substitution, you only have 2 resonance structures because these don't count to 4 at all. So all other deactivators are 3 directing. And here's just the list of them, and in a list of relative deactivating, destabilizing effects. You've got strong, you got strong, you got strong, and then you got very strong. Put a nitro group on a benzene ring and you pretty much really deactivate it towards further reaction. So lots of information here. This is probably the most important thing to take away with you in terms of applied memory, applied knowledge, but it would be nice if you understand why these are as they are.